It is my pleasure to introduce Professor Jablonowski, who is an associate professor in the Department of Climate and Space Sciences and Engineering at the University of Michigan and the head of the Atmospheric Dynamics Modeling Group. She received her Master of Science in Meteorology from the University of Bonn, Germany, and obtained her PhD in Atmospheric Science and Scientific Computing from the University of Michigan. She was a postdoctoral scientist at the National Center for Atmospheric Research and NOAA's Geophysical Fluid Dynamics Lab, and worked as a consultant at the European Center for Medium-Range Weather Forecasts in Reading. Her research lies at the interface between atmospheric fluid dynamics, scientific computing, and machine learning. In particular, her work focuses on the dynamical core of global climate models and how they couple to physical parameterizations. Professor Jablonowski is a recipient of many awards, including a Department of Energy Early Career Award and the Presidential Early Career Award for Scientists and Engineers. She is a member of the Steering Committee for NCAR's Community Earth System Model, a co-chair of the NCAR CESM Atmospheric Model Working Group, and a co-chair of the NOAA Coupled Model Development Group for the Unified Forecast System. And in addition to all of this, she's also a member of the American Meteorological Society Committee on Artificial Intelligence Applications to Environmental Science. Today, she will be presenting recent work on evaluating machine learning approaches for physical parameterization in a global climate model hierarchy. And with that, thank you for being here with us today, Professor Jablonowski, and I'll hand it over to you.
Thank you for the invitation to present here during the US TIVAR Data Science webinar series. It's my great pleasure to introduce our work. And this is work with my student, Garrett, who you see here in the photo. And this is me, of course. And we are looking at machine learning approaches, various machine learning approaches for GCMs. And you will see here in a minute what this is. So let's start with some overarching questions, and basically, can machine learning methods replace or augment physical parameterizations in atmospheric GCMs? How well can machine learning method mimic physical processes? So we ask questions: are they realistic? Are they representing the right dynamic range? Are they efficient from a computational viewpoint? How does machine learning performance depend on the data selection, on the resolution even of the input data, the machine learning architectures and the hyperparameter choices? And this includes new work that we did with the tool Rsquare, which is a hyperparameter tuning tool that was developed at the University of California, Irvine. And last but not least, how can we embed physical constraints into the machine learning algorithms? So these are a whole bunch of questions. I only have half an hour, so I will only answer some of them. So let's start it. Okay, for those of you who are not quite familiar with atmospheric models, I just want to give you a 1-minute introduction to GCMs and what they entail. And here in this depiction, you see the globe, you see the grid system. It's a latitude-longitude grid, and this is basically the core, which we also call dynamical core. So here on those grids, we solve the hybrid, the primitive equations. For example, these are coupled equations of momentum, thermodynamic equation, ideal gas law, and so on. So these partial differential equations are solved on the model grid, and of course it has a vertical dimension as well. Nevertheless, there are many things that are slipping through the cracks of such a big grid. The big grid, I mean like 100-kilometer grid spacing. There are many processes, for example, like friction or precipitation, that are way smaller than a 100-kilometer scale. And these are parameterized, and this is then denoted here in this little side box. All these physical processes that are way too small are parameterized, and this happens typically in the vertical columns that you see here, aligned here along my mouse. So the question that we are answering today is, how can we mimic these physical parameterization in the vertical column with machine learning approaches? And we are not doing it quite yet in the full complexities, in a full complexity simulation. So we are restricting ourselves to a slightly simpler model hierarchy. And the model hierarchy is depicted here by these boxes. I will really focus, dive here into the middle box. So this hierarchy denotes a typical testing hierarchy where we start with 2D shallow water models, even dry models, test the dry dynamical cores before we really go to the 3D complex simulations, either in AMIP mode with prescribed boundary conditions or fully coupled. So here in the middle box, we are now using the dynamical cores with really simple physics that can be dry simple physics or most simple physics. And what I mean by that is denoted here. So there are these two, we can also call them test cases. One is called the Hertz-Rarus test case. The other one is a moist version of this Hertz-Rarus test case that we worked on a couple of years ago. I will show you here in a minute how these look. Before I show the equations of these test cases, let's take a really quick look at the equation set, and this denotes or highlights what I'm adding, what the machine learning algorithm is actually adding to the equation set. So I'm basically answering the following question: can machine learning replace those circled, well, here it's just a forcing function basically. Can machine learning replace these forcing algorithms, physics forcing, for example, momentum or the thermodynamic equation, or here the moisture equation? So these are the targets, especially the thermodynamic equation is my target, which determines the time tendency for the temperature. And the Hertz-Rarus, and this is now the so-called dry simple test case, the Hertz-Rarus test case, goes as follows. It's really, really simple when you look at the equation set. It's a Newtonian temperature relaxation with the dt function here. And Newtonian means that I'm relaxing my temperature to a prescribed equilibrium temperature. And then I have a Rayleigh friction. This is the function here, basically friction coefficient times the velocities. So this is a very linear algorithm or a function, as you see, and this is slightly nonlinear. There's a coefficient in front. These are relaxation coefficients. So here in the dry case, you can ask the question, can machine learning mimic those rather simple forcing mechanisms? And we are exploring neural networks and random forests for this question. Well, in the end, this may be too simple, and my second element of the hierarchy is a moist version of the Hertz-Rarus test. And how does that look? Basically, let's split this up. So we are starting with some very simple physics, which we published in Reed and Jablonowski a couple of years ago. What this is that we have some surface fluxes of sensible latent heat and momentum that are coupled to the ocean condition and the conditions of the lower atmosphere. In addition, we let it rain, and we let it rain via large-scale condensation. This is as simple as 100% relative humidity lets it rain. We basically take out the supersaturation. There are no clouds that we keep. We just let it rain out instantaneously to the condensation level of 100%. And then we have some PBL mixing. So this is in the planetary boundary layer of potential temperature, moisture, Q, and U and V with the two velocities. Plus, this is the Hertz-Rarus part, we have some temperature relaxation. So this is the Newtonian temperature relaxation. And this is also coming from Hertz-Rarus. There's surface momentum flux there. Surface momentum flux is basically the Rayleigh friction that we just saw. Now you see that I'm actually double counting the friction. So friction is coming in through the Hertz-Rarus functionality and also here through the simple physics function. So in order to eliminate the double counting, I get rid here of one of the forcing functions. And this is a makeup of what we call the moist version of the Hertz-Rarus test. And to make this even clearer, we basically can just show you the equation set. We can augment, let me point you to the thermodynamic equation. We can augment the thermodynamic equation here with, this is a temperature relaxation. We have condensation. This is a precipitation. We have PBL diffusion, mixing of temperature in the lower boundary layer. And also we have surface fluxes, sensible surface fluxes that determine the temperature tendencies. In addition, and also look here at the precipitation rate. We want to mimic, these are the two targets basically for our machine learning approaches. We can also mimic with machine learning the precipitation rate. And that is actually somewhat more complicated. We basically need a vertical integration over all model levels or in the pressure domain in the vertical direction of the condensation rate. And the condensation rate is non-linear. It depends on supersaturation. And again, we take out supersaturation via large-scale condensation. This gets integrated, and this makes up the precipitation rate. Basically, how much does it rain per day? How many millimeters, basically. So in the moist case, we are asking the question, yeah, can machine learning, and again, we do neural networks and random forests mimic the physics time tendency that is circled here in the upper box, and also the precipitation rate. And let's take a look how well we can do that. Before I show you results, I do need to spend a few minutes to just explain the general framework. What I mean by that is, which model are we using to train the model? What is the resolution? Which are the input? What are the input parameters? What is the design of my machine learning architecture? So I would call this housekeeping. I keep this rather short, but it will be there for you to view whenever you want to take a deep dive. You can just stop the video later if you watch it on YouTube and really take a close look at the design issues. Okay, let me get started on that. So we are using as our tool in the model hierarchy, we are using the NCAR Community Earth System Model called CSM version 2.1. This is a recent version. That version contains the so-called community atmosphere model, which is basically the dynamic core plus the physical parameterizations for the atmosphere. The model also comes with a few choices. For example, the dynamical core can be chosen. Here we choose the so-called finite volume dynamical core in the community atmosphere model, which is called COM6. And it's a rather coarse resolution. That means like 2 degrees. It's not quite 2 degrees as you see, but let's call it 2 degrees. It has 30 levels in the vertical. And we let the model run for about 60 model years. This has a reason, which I come back to. We also had runs with different model years and different output frequencies. You will actually note the output frequency is only once per week. We are collecting output on U and V, the velocities, pressure, temperature, the precipitation rate, and the time tendencies. These time tendencies are used for training purposes. They are basically our grounded truth. These are the time tendencies that the heterogeneous forcing or the most heterogeneous forcing give us analytically. So again, the question is, can machine learning mimic the analytical functions that the model actually saw? So from the 60-year time sequence, we use about 50 years for training and validation, like 40 and 10. And we use about 6 years to test the model. And you kind of see the timeline. We have a gap, which is maybe a little wide. 4 years is not needed. We need to keep the data separate. There's no, just also for you know, not familiar with those test cases, there's no annual cycle in these models. There's also no climate change signal in these models. So all those data in all years are equivalent. They are representing the same climate, the sample, the same distribution. Okay, just a quick note, with that configuration, we have about 36 million columns. So it's, you know, quite a bunch of data, and each column contains 30 levels, as we see here in this picture. As I mentioned, we want to use neural networks and the random forest. And this is, of course, a schematic view of neural network or random forest, a machine learning approach. Of course, you might note here, I painted it as a black box. In the end, it shouldn't actually be a black box, but for today's talk, I'm not opening that black box and I'm not trying to explain the processes that we are seeing and learning in our machine learning algorithms. So plainly, just really from a high-level viewpoint, there's input that goes here into the machine learning algorithms, either neural network or random forest, and we see some output. We use scikit-learn, Keras, or TensorFlow, and this is very new for us. We now optimize our selection of hyperparameters, the machine learning hyperparameters, with Sherpa. This is a new tool. Here I point to a paper and also a GitHub repository if you want to take a closer look. Okay, before I show you the results, again, a little bit of housekeeping to make it transparent, our process. Currently, all the training and testing is offline, so we are not coupling yet back into the model. So this will be our next step, of course. We are training different machine learning models for the temperature tendency and the precipitation rate. They're not trained at once, yeah, they're retrained. And in terms of data preparation, we are sampling, or the samples, the time samples are grouped into vertical columns and reshaped. Here, as we know that, the vertical columns are left together. And we also project the data onto a -1, +1 range. This is the subtraction of the mean at each level and also the division by standard deviation and rescaling at the very end. Data are shuffled during training. This is true for the validation and the test data. Not test data, the training data and the validation data. Okay, two more slides here on the neural network architectures. This denotes input features. And this is now for the dry case, a Hertz-Virus dry case, which is pretty simple as you had been seeing. We only use the temperature, the pressure, and the latitude as input, and the output will be the forcing, the temperature forcing at each level. Here I list a whole bunch of the hyperparameter choices. I will not read them to you, but they're there for your later evaluation. It's a small network. The dry model is not very complicated, so a small network should be able to capture the essence of the forcing structure. In addition, and this is now the neural network architecture of the moist model, the moist Hertz-Virus model, where we predict the moist tendencies, temperature tendencies, and also the precipitation rate. The features are now more complicated, the input features. They also include Q, the moisture, and the surface fluxes. And output, again, is either the temperature tendency or the precipitation rate. We have bigger networks, as you see here, and they're varied depending on the temperature or the precipitation rate. And again, I'm listing here the details of the hyperparameter choices for your later evaluation. Okay, and this is really my last slide before I show you the results. This now explains the settings, the hyperparameter settings for the random forest. And again, these are optimized via Sherpa. This was also true. We actually just point this out. The learning rate and also the dropout in the neural networks, they were optimized via Sherpa. And we optimize even more parameters here in the random forest configuration. You see here the choices. Again, I'm not reading them to you, and you'll have them here later at your disposal. All right. Let's dive into the results and really take a close look. I start with the dry results, and I'm showing you now the averaged, this is time average, zonal average of the dry test data. So let me ask a question, basically, this is the model, these are the forcings that the model has, the Hertz-Virus model. This is the machine learning forcing that the neural network and the random forest, here in these two columns, rows that they learned. You see, this is now, of course, an eyeball norm comparison. You see that they mimic each other quite well, but when you look here at the difference plots, you also see these systematic differences. So what are these? Let's take a closer look. Again, these are zonal mean, time mean plots over the test period, the 6 years. We can definitely see, again, looking here at the middle column, that both machine learning algorithms learn well, learn the forcing well, but that there is a systematic, also want to just kind of direct your eye here towards the range. All the differences here are positive. So there is a systematic positive biases in both the neural network and the random forest. We assume, this is not quite proven yet, but we assume that we are actually battling some overfitting issues here in our configuration, which leads here to these positive biases. These biases are small, I should say. Yeah? So when you just look at the magnitudes here in Kelvin per day, but they're systematic. And so this needs to be evaluated a little bit further. And of course, now you ask the question, well, you know, the dry model, that's pretty simple. So let's spice it up. Let's make it more complicated. And yes, you're right. So let's take a look at an increased complexity. And what I mean by that is the most tendency, the most temperature tendencies. Again, we are seeing in the first column the community atmosphere model. Of course, these are the same plots, the time means, zonal means of the most model. And in the middle column, we see the machine learning algorithms, here the neural network at the top and the random forest at the bottom, and the differences here in the last column. And this gets more interesting now. As you see, the random forest is actually mimicking the forcing rather well. And you can even argue, you know, we can look here at some of the details. We are capturing, for example, here these negative regions quite accurately. We are also capturing, and this is a striking difference, of course, to the dry simulations. We are also capturing the strong peaks, heating peaks here in the temperature. They come from the precipitation peaks that come with in the moist model that are located here in the tropics. But, and now there is this big but here in the neural network. You also note that the secondary heating peaks here in the mid-latitudes that we see in the CAM model are missing. And this is, of course, denoted and highlighted here by the differences. So this is a striking omission. So there was something in the neural network that prevented it from learning the mid-latitudinal signatures. The tropical signatures were captured, but of course, again, not perfectly. You see in both simulations that the magnitudes are diminished of those heating peaks here in the tropics. Bottom line, the random forest in the current configuration here outperforms what the neural network had learned. So that's something to keep in mind, and it's confirmed in some of my other graphics that I will show you now. Basically, just to highlight this even better, let me just single these out. Here you see now the neural network and CAM, and this is at various pressure levels at 950, 850, 400, and 200. You see the deficiencies, especially here in the mid-latitudes, that the neural network here in red and in green is missing out here on those signatures in the mid-latitudes, also, of course, here in the tropics. This is, when I go to the random forest, we already figured it looks better from our previous depiction. And the random forest in the same configuration, we are plotting here the signatures of the forcing at 950, 850, 400, and 200. That is actually met quite well. There are deficiencies, yeah, there are these deviations as I'm pointing here with my mouse. Also, there are these deficiencies here in the peaks, here in the tropical area, but they are less pronounced. And an eye test, and this kind of closes that argument, an eye test, and this is a random snapshot, I just picked one out of the test data. This is at 850, you see the community atmosphere model, this is a truth, the neural network and the random forest, and you see that those heating bands, these are aligned, of course, with precipitation bands, are actually captured quite well, as we figured already in the random forest, but they are really missing here in the neural network. That's, of course, depicted in the difference plot as well. So the question is that the end of the story? I will tell you no, it's not. Yeah, it's a deficiency in the current in the current model, in the current configuration of the neural network, but it's not a general efficiency, as I hopefully can convince. Okay, before I jump into precipitation, which really makes that case, I thought it's informative to also look at the R-square. This is basically a correlation measure. And here is the R-square. If you want to look or see how it's computed, I presented here the equation set, how this is computed. In the end, you want basically all red. Yeah, you want R-squares to be 1, which is a perfect correlation. And in the random forest, it is actually really, really high in a big area here of the domain. And in the white spots, you see actually negative R-squares. There's basically anti-correlation happening in those areas. So yeah, that's what we confirmed already. R-square is in the neural network is, well, it's performing okay in the tropics, but has these big deficiencies in other regions, and random forests outperform this. It's sometimes when you look at those R-squares and you know, used to looking at these, it's good to maybe also see other R-squares from the literature. And there's one that is very informative and related here to our study. This is from a study by O'Gorman and Dwyer from 2018. And here you see an R-square of a random forest emulation that they did with an aquaplanet. So it's actually quite comparable. It's even a little bit more complicated than our assessment. And they also plotted the R-square of the temperature tendency. And just to kind of really put this into perspective, of course, the color scales are different, but we have very, to some degree, similar signatures, maybe even a wider range of positives R-squares in comparison here to the O'Gorman study. So that's encouraging that the random forest captures these large areas at really with good performance. Okay, there's also some negatives, and this is now related to the precipitation rate. And this is in the neural network, which already saw these deficiencies in the mid-latitudes, didn't really learn the heating rates that well. And that's also true, and it comes together really in our configuration. That also is true for the precipitation. So when you look at the precipitation rate learned by the neural network, you see these big differences, and that's especially highlighted here in the tropics, also here in the mid-latitudes, where the neural network does not really learn the precipitation that well, also shown here in that tiny snapshot of the precipitation rates. Well, I could stop here and basically tell you neural networks don't work as well, but that's not the case. We had, in the past, we had better configurations, and here I'm referring to a 1-degree simulation, which is a finer resolution, of course, than the 2-degree. But here, the same comparison is actually matching really well. So here, the neural network and the 1-degree community atmosphere model match really well. We have small deficiencies here in higher latitudes. It's also true when you compare these similarities are also evident here when you compare these panel plots. There are many, and I skip over this to really close this talk. I skip over this, the details here of the 1-degree neural network configuration. Just want to point out before I do that, one thing that we should keep an eye on, and this is actually these white spots that can appear in the neural networks, and the white spot is actually negative, and that should not be the case. Negative precipitation is, of course, unphysical, and this needs to be watched out for in future versions of those neural networks. Okay, I skip over the next 2 slides. You can go back to them later. These explain the configuration of the 1-degree model simulation and the 1-degree neural network architecture. The interesting part I want to close with is the performance of this precipitation rate in the 1-degree simulation, and I really call this promising. The 2-degree didn't show this to us, but again, this is in our assessment a matter of further tuning of hyperparameters. But when you look at the 1-degree, and this is a little animation that really lets you compare the snapshots, individual snapshots of the community atmosphere model, the precipitation rate, versus the precipitation rate that the neural network learned. So down here in the lower plot, we see the learned precipitation, and we can compare it here in our eyeball norm with the actual, the truth of the precipitation rate. And as this runs over, this is about a month or so, you see very good similarities, even here in those sharp bands, in the precipitation bands, and both the strength is well met in those configurations. And this is really a complicated parameter to learn, which I mentioned, this is actually an integral, a vertical integral of the condensation rate. Again, to close, this just denotes again a different depiction of the precipitation rate. Here, the machine learning along the y-axis and the model precipitation rate here along the x-axis. If you align them, and these are just 10 time samples just plotted, ideally everything should be along the one-to-one line. You see some spread. This is undesirable, of course. We are not perfect. We also see, even here in the high precipitation range, we see points that are very much aligned here along the blue line. And we see these slight negatives, which are, of course, of concern to us. Okay. And let me wrap up with just a few thoughts. One thought is, and this was an idea that has been published lately by Jonathan Wine and David Wren. They had the idea that we maybe shouldn't actually use the data on the Lat-Long grid on a sphere, but we maybe should use data here on a cubic sphere grid or some other grid that is more uniform. This basically kind of denote here the meridians in a Lat-Long grid. They cluster here at the pole points. Basically, we have a lot more resolution here at the pole points, which is not needed, maybe not desired even for machine learning approaches. And that's not the case when you project data here onto these cubic sphere geometries, which are now becoming very popular in the climate sciences. Okay, so let me summarize and maybe just end with a few comments on ongoing work and questions on future work. So we asked some very fundamental questions. Is random forest better, worse than neural networks? What is a good selection of the data? Should we go with, for example, weekly output data to train, or should we go with 3-hourly data, like in the 1 degree case, which is highly correlated spatially and in time? So we really wanted to explore, and we are not quite finished yet, but we are going to explore this arena further. What is the best data selection? So both, I guess we saw both neural networks and random forest, they show skill and they learn. We are not making claims these are the ideal configurations. There is further room for tuning. Also for smart data selections, maybe even the cube sphere data idea. We started also evaluating other data layouts, not just the vertical columns that we saw for the physical parameterizations. Can we maybe use the horizontal data layouts for the machine learning algorithm? Should we train one network for all predictors, or should we train individual networks? Currently, we do individual networks for precipitation and moisture, precipitation and temperature, but maybe we can do this together in the future. Does the spherical geometry interfere? What is the resolution sensitivity? We saw 1 degree look better in the precipitation assessment, but that's not a statement that it's due to the resolution. It's a statement that's connected to the resolution and hyperparameters, of course. Okay, and let me close with some future work. So we want to further improve the accuracy of the machine learning models. That further includes hyperparameter tuning. We started exploring boosted forests, XGBoost, and also CNNs, convolutional networks. We want to couple the networks back into the community atmosphere model in an online mode, and that brings up questions concerning the stability of those coupled models. We want to enforce physical constraint. Basically, we don't want negative precipitation, and this really advances these ideas of physics guidance. And we want to explore transfer learning. For example, can we learn at low resolution and then use pre-trained networks at high resolutions? And of course, go further in the complexity in the hierarchy and maybe go to the upper planets or even AMIP or coupled runs. Okay, let me stop here, and I'm happy to entertain questions.
Thank you. I think we'll take the next 15 minutes for questions. So a reminder, if you have a question, use the raise your hand, or you can type your question into the chat box. So with that, I do see a question from Pierre Gentine. It says, hi, Christiane, very nice presentation. I wonder why is the NN underperforming compared to the RF? Use Sherpa, so it should not be a hyperparameter tuning. Any idea where this would be coming from?
Yeah, I should say we used Sherpa to learn something about the dropout and the learning rate. And there are many other parameters Sherpa could help us with. So we can't claim that we used Sherpa extensively for the neural networks. For example, it didn't inform our selection of the number of neurons and number of layers. I think that will be the key. Also, this went quickly, but there was a different architecture in the 1 degree configuration where the neural network learned quite well in terms of number of neurons and number of levels. So I don't think we have exhaustively understood what Sherpa can still give us. So there's more work to do.
He says, thanks a lot. I was indeed wondering about the depth of the NN.
Yeah, I listed this when, you can later go back, or I can just maybe just go to a few of those slides. So in the 2 degree case, it's a few layers. They have a different number of neurons, and they also differ depending on either temperature or precipitation. And this is now for the coarse resolution, the 2 degree. For the 1 degree, we have more neurons because, of course, the data is bigger, the data volume is bigger.
Thanks a lot, Christiane.
Any other questions? There's a comment from Noah Brenowitz. For online tests of emulators, you may want to check out this library. It's a GitHub library. I cleaned this up a bit, so it should be easy to use. I'm happy to help.
This is awesome, Noah. We do want help because we started looking at options like Pritchard has also put forward. I think he calls it the Keras Fortran Bridge. This is a product, maybe Noah is familiar with that, that maybe can help us with the coupling. And Noah, I know you have been doing this in a different framework. And yes, we would very much like to learn from you how this is done and see how easy or complicated it is. Unfortunately, we are not seeing yet, I would say, a convergence of those coupling infrastructure pieces in the community. So I know David Gagne had also worked on some homemade solutions and others probably. And yes, I would very much like to get advice on that.
Okay. And Noah is a working group member, so I can probably connect you two after this.
Perfect. Yeah.
All right. A question from Oliver Wattmeyer. Have you explored sensitivity to sampling of training data, for example, using weekly outputs versus 3 hourly?
Yeah, unfortunately, I don't have that particular comparison plot here, and I can't comment on it. We actually explored this last week. So our decision to go to weekly output is kind of a last-minute decision because we were getting concerned with the correlations in 3 hourly data. That means temporal correlations, because over 3 hours, you saw in my, for example, in my loop of the precipitation, these were 3 hourly snapshots. It's still rather, the precipitation bands, they travel rather slowly, even with a 3 hour time step. So if you have 3 hourly output, there aren't too many differences from time step to time step or snapshot to snapshot that you sample. So in order to decorrelate, and this now refers to the temporal range, we thought a week is probably too much. Yeah, I think 2 days maybe would also be, or 3 would actually do the trick. We went ahead and we ran basically 60 years of that simulation to get weekly output. We do have the 3 hourly output still on the disk. I don't have the plot yet, but I'm happy to send this to you. That probably will be done next week. So I have this really direct comparison of the two. There's also, and I'm not 100% certain how to address that. We worried about spatial correlations as well. Again, the idea is as you go from one data point to the next, even on a 2-degree grid, there are lots of correlations in the spatial domain. So maybe there isn't enough new information when you just use all the grid points. So we started coarsening, actually with like factor of 2 or 3, the coarsening the input data. That led to some surprises, and this was also last week. That really was unhealthy for the random forest. You couldn't, especially in the latitudinal direction, you should not coarsen the latitudinal spacing. We were able to coarsen in the longitudinal direction, which is more symmetric, because there's also no difference between land and sea masses. So each longitudinal point is basically equivalent. That seems to work, although we kind of shied away from that idea again, of course, in the spatial domain. So I don't have the full answer yet, Oliver, but I'm happy to hook up and tell you later.
Any other questions? Okay, Oliver says, thanks, sure would be great to chat more.
Yes.
Andre Perkins says, you mentioned you were considering training and configurations other than column-wise. Could you say a bit more about what you were considering?
Well, especially for convolutions, we thought it might be advantageous to go layer by layer. So currently we basically keep the columns together, 30 data points in one column. Convolutions don't help you that much. You know, you have 30 points, but once you do convolutions, it's basically, compresses the data down to smaller dimensions. There isn't a lot to work with. So we thought there, of course, and this comes back maybe to the dependencies that are in the data anyhow in the spatial domain. Maybe it will help us once we go to CNN, convolutional neural networks, to do it, instead of feeding into the machine learning algorithm these columns, maybe feeding in these layers by layers and then use convolutions. We have the ability to configure or reshape in any form. So it can also be scribes of longitudes or scribes of latitudes. Not certain that, at least I'm not aware of anybody who started exploring this. I'm only aware when I kind of read the literature of people that do the column feed. Yeah, so most people that look at the parameterizations do the vertical columns. And if you know of other approaches, I would be happy to learn about that, just to see what the potential outcome or potential benefits could be of these other data layouts. So I can't give you a full answer, but this would be our first approach to go layer by layer.
Another question from Noah. Do you have any idea how long the training simulations needs to be? Could you get away with a 1 year / month / day of training data?
Well, yes and no, I guess. So we have currently, when we look at, and now I'm counting the number of columns basically. So in the 1 degree case that looked really good for the precipitation, we had 1 year of training. We ran the model for 2 years, so this was way shorter, but we produced the output every 3 hours. So with that, we ended up with, I think, about 150 million or so columns, usable columns for the training step. And then another 150 million that we had, this was really just for 1 year, and another 150 million for validation and testing. On the coarser grid, we went with 60 years, but only weekly output. Actually, the number of samples, I think you saw my calculation, is way smaller. It's also coarser resolution, but the number of samples there was only 36 million for 50 years. And then we had another 10 years or so for testing. I think this is the crux, and I would love to also get some more insight here from this group. This intuition, how much is enough, is very hard for us. I think we are mostly, well, not everybody here on this call, but I guess we are probably mostly trained here as atmospheric scientists, climate scientists, and not necessarily as machine learning scientists. And we are merging the fields, which is an awesome opportunity, of course. But it's very hard to get the intuition. to know these answers. How many data do we need to do the job well, and when can we stop? I think this, maybe if this group has an opportunity here to, maybe provide those answers to the outer community. Maybe even one could envision maybe best practices like a paper or some other document that would document all these choices that we make. This is, to some degree, the troublesome fact. When you read the literature, you see the best ever configuration that these people produced, but you never see maybe the many failed attempts, that the many hyperparameters that didn't work. Yeah, and I think it would be actually very informative to also document that to some degree, to help us as a community to learn quicker.
I think there are some comments now in the chat box. Here's a question from Ankar Mahesh. Does the 1 degree resolution have higher precipitation peaks, making it harder for the NN to reach a loss minimum by consistently under-predicting?
Yeah, good observations. Yes, the higher, just stick to this a little bit. And it depends how you look at it. Yeah, when you look at the instantaneous snapshots, we have very high, and this is saturating the color scale. So there are even higher. You saw in my line plot. Was it here? You saw that you can go up to 600 millimeters per day or so in extreme cases. Yeah, this very much depends on the resolution. At the coarser resolution, you don't get as many of those and not as high. These precipitation peaks will be diminished. Will it determine how well the machine learning algorithm can learn? I'm not convinced. I think we should be able to train the 2 degree as well as we train the 1 degree. I think it's currently a matter of our hyperparameter choices, and Sherpa might help us further with the right selection. As I mentioned, we only use Sherpa for the dropout, which is trying to avoid overfitting. And overfitting is another concern of us, that we actually, even at the 2 degree resolution, that we are overfitting in the training process. It's not quite clear yet how much, but we definitely saw that some dropout helped.
Okay, and I think Garrett has a comment for Noah. For the random forest, we tuned the N samples with Sherpa and found that it liked close to the maximum number of samples, about 25 million. This was already shuffled training data, though, so not exactly an answer to your question, but I thought it could be relevant. Garrett, did you want to unmute yourself and talk a little bit more about this?
No, you read it basically how I wanted to say it, so I think I'm okay. I just wanted to give it a little bit of an extra note there.
Yeah, and Garrett was, of course, the person that explored all these parameter ranges, so credit to him.
Okay. Do we have any final questions? All right, I think that will end our open session of this webinar. So thank you, Christiane, for your presentation. Also to Garrett for your work on this research. As I said earlier, a recording will be shared later this week. Coming up in 2 weeks on December 7th, we will have Amy McGovern of University of Oklahoma present in the webinar series. So until then, feel free to reach out to me if you have any questions about the working group or about US CLIVAR in general. So thank you all for joining.